So currently we are discussing about predictions for SISO model, that is single input single output model. This discussion is not completed. Here we discussed about I think you are remembering that initial block diagram of model predictive control system. So we have a plant, right? Then we have a model also. We have a model and we are giving the same manipulating variable u of k to these two system. So this is giving the output of plan, that one is actual output y of k, and what we are doing, we are predicting the output of the system. Okay, so this is y cap of k. Actually, there is no need to predict the current value that is already available. We have to predict the next values. So, for example, if k is the current instant, then we have to predict y cap of k plus 1. Y is small letter, then k plus 1 means we are predicting the next value of output. It is known as one step ahead prediction. Then we discussed about y cap of k plus 2. It is known as two step ahead prediction. Means if k is a current instant, then what is the output after 2 instant? That is two step ahead prediction, etc. etc. We discussed about y cap of k plus j, means j step ahead prediction. Now using this we can generalize this. The last prediction that we have to perform is y cap of k plus p. Okay, so these are separately, we are separately predicting this p prediction k plus 1, k plus 2, etc. up to k plus p. Now we have to generalize this one. Can we simultaneously predict all these values? Definitely we can possible. Okay, and we can represent the simultaneous prediction of output from one step ahead to p step ahead. We can represent it by using a vector, and we can represent it as capital Y cap of k plus 1. Okay, means in the next instant, k is a current instant, and we are predicting the p next value starting from 1. Okay, that is the indication. So y cap of k plus 1, where y is a capital letter, means we are predicting p next values at the same time. It is known as the p horizon or horizon p prediction. Okay, the length of prediction is p. Okay, now at the same time we can estimate the m manipulating variable including current instant. So that is u of k minus 1, etc. up to u of k minus m plus 1. That is from the current instant we can predict, we can utilize m inputs. It is known as m horizon input. So we can label it as capital U of k. Okay, means how to generalize this. That one is the next thing that we have to discuss, that is multi prediction. After multi prediction, so this is one remaining thing, multi prediction in this chapter. Okay, after multi prediction, then we have to discuss about, see here, the model is exact representation of plan. Now in first class or in first section, I told you if this plant is affected by disturbance, but some disturbances are measurable. Some disturbances are measurable. If the disturbances are measurable, we can include or we can consider it as an input. But there are some disturbances that is not measurable. So definitely the model is not affected by that unknown disturbance, but plant is affected by unknown disturbance. So definitely y of k is not equal to y cap of k. So there is a difference between these two, where this is plus, this is minus. So by using this one, we can call it as b. This is bias, the difference between these two, bias b of k plus 1, b of k. So using this b of k, we have to correct this y cap of k. So the correction of prediction using this difference is known as the corrected prediction. We have to label this one is p horizon prediction. The same p horizon prediction that we have to modify by using this bias. That is represented by using y nu of k plus 1, which is corrected by using this b of k. Please note this is vector, but b of k is a scalar quantity, so we have to convert this b of k to this vector. What is the size of this y cap of k plus 1? We have 1 into capital P. P elements are there. So we have to multiply this b of k with I in such a way that P b of k are generated. So all elements are 1, but this one is duplicated. So P b of k are generated. Okay, so that one is the method. So after all, we are modifying y cap of k plus 1 to y nu of k plus 1. So that one is correction. After correction, then we need the matrix representation of the equation. We have an equation. So that one is an analytic equation. So we need a matrix representation of that equation. So that one is the next thing that we have to discuss. After that, we have to start the next section, multi-input, multi-output system. In multi-input, multi-output system, here we are considering only one input, and out of that one input, m values are used. Now, what about if you have r input? If you have r input, so this is 1 by m, such r inputs are there. So the size will become r into m. This size of u of k. Similarly, multi-output. Here we are considering only one output with the p prediction. Now, such small m output variables are there. So the size of this vector will become m into small m into p. Don't confuse with this m. This is small m means number of output. Capital M means the horizon of input. Okay. So what will be the thing that we discussed under predictions for scissor model? We are using the same equation with a slight modification. The size of the vector, size of the matrix, etc. will change. Okay, so that we are going to discuss in this section. So multiple prediction. So vector of predictor response for next p sample instance can be written as y cap, capital Y cap k plus 1. That one is a vector representation of the next p samples. That is equal to column vector y cap of k plus 1, y cap of k plus 2, etc. y cap of k plus p. Okay, y cap of k plus 1 equal to y cap of column vector y cap of k plus 1, y cap of k plus 2, etc. y cap of k plus p. So note it as equation number 25. Now the vector of predicted unforced response. We discussed about the unforced predicted response. So that we can write it as y cap 0 of k plus 1, that is equal to column vector y cap 0 of k plus 1, y cap 0 of k plus 2, etc. y cap 0 of k plus p. Equation number 26. Now we can define delta u of k, capital letter U, delta u of k, the input horizon, that is equal to column vector delta small letter u of k, delta u of k plus 1, etc. delta u of k plus m minus 1. In previous discussion, I had written it as k plus m, k minus m plus 1. That is wrong. I am very sorry. K plus m minus 1, because the next input, not the past, future input that we are calculating. So delta u of k equal to column vector delta u of k plus 1, etc. delta u of k plus m minus 1. Okay. Now the control horizon m and the prediction horizon p are the key design parameters. Please note, while designing the model prediction controller, the two important key parameters are m and p. In later section we will discuss about how to select, or what are the selection criteria of m and capital P, or is there any constraint, that we will discuss in our last section. Okay. So in general, please note, in general the control horizon m must be less than or equal to prediction horizon. Control horizon must be less than or equal to prediction horizon. And one more thing is the P must be less than or equal to n plus 1. P must be less than or equal to n plus m. Okay, so these two are very, very important. M must be less than or equal to P and P must be less than or equal to n plus m. Okay, so definitely P is greater than or equal to n, because m is less than or equal to p means p is greater than or equal to n, definitely. Okay, so these are the criterias. Okay, so model predictions can be written in vector form. So now we have the vector representation. So model predictions can be written in vector form as y cap of k plus 1 equal to s into delta u of k plus y cap 0 of k plus 1. Okay, uh, so we can, here we have a term S, that S is the P into M dynamic matrix. Okay, P into M dynamic vector. The reason is this is M by 1. In previous section I had written it as 1 by M. I am very sorry. It is M into 1. I am very sorry. This is M into 1. This is P into 1. So how to convert this m into 1 to p into 1? How to map this m into 1 vector to p into 1? By using S, which one is p by m. So S is the p by m, it is known as the dynamic matrix. S is known as the dynamic matrix. So that is equal to, that S is equal to S1 0 0 etc 0, S2 S1 0 etc 0 etc etc, Sm minus 1, Sm minus 2 etc S1, Sm plus 1, Sm minus 1 etc S2 etc etc. Last row is Sp minus 1, Sp minus 2 etc Sp minus n plus 1. So we all are aware about what is, we all know what is S1 to Sp. These are the step response coefficients. We already know how to find it. S1 to Sp are the step response coefficients. Okay, so we can write the dynamic matrix as this one. It is very easy to remember this one. The first element, if you are taking first row, first element is S1 and all other elements are 0. Now what about the second row? Second row is starting from S2, then S1, then all other elements are 0. So what about third row? S3, S2, S1, all other elements are 0. Okay, so at a particular row, the all zeros are vanished. It is starting from S1. When it is starting from Sm, the last element is S1. So please note, if a particular row is starting from Sm, then the last element is S1. There is no 0. Okay. Then, if you are going downward, the next one is Sm plus 1. So definitely this term will become S2, because this one is a last row element. Okay. Now we can go up to Sp. So Sp, Sp minus 1, Sp minus 2, etc. Sp minus m. It is very easy to remember this one. This size is m. In a particular row, you can see m elements. In a particular row, the number of rows that you can see is p. So say if p equal to 3 and m equal to 1, then you can see 3 rows and 1 column. It is very easy. Okay. If the given problem is, if you are asked to design a model predictive control with 3 output horizon and 1 input horizon, then the size of S is 3 by 1. So please remember that. Okay, it is very easy to remember. Already it is starting from S1. Okay. Now after in mth row, in this particular first row itself, if m equal to 1, in mth row, the first element is Sm and last element is S1. Now what about the last row? It is Sp, then up to mth element. The last one is mth element, that is nothing but Sp minus m plus 1. Okay, so it is very easy to remember this matrix. It is known as the dynamic matrix. Okay. Now, so please note, this one is the vector representation of the model predictive control, or the multiple prediction. If you are predicting p output variables at the same time, it is known as multiple prediction, and this one is the analytical representation of that multiple prediction, where S is known as the dynamic matrix. Now we are going to correct that difference between the actual output and the predicted output. So output feedback and bias correction. So the cumulative effects of modern inaccuracy and unmeasured disturbance can lead to inaccurate prediction. The two problems are there. First one, some disturbances not identified. Disturbance is there and we are unable to measure it. Second one is we wrongly modeled the system. If you are selecting an RC network, that R itself, if you are selecting a resistor, in resistor itself you can see error. Some error will be there. If you are selecting 1 kilo ohm, it may be 970 ohm or it may be 1010 ohm. So some error will be there. Is it okay? But if it is resistance, we can a little bit we can accurately measure that value. But in real life, in several components, you can see some variation. So it is known as inaccurately modeled system. So we have to expect that. Similarly, we can see some unmeasured disturbance. So definitely these two will lead to an inaccurate prediction. So by using the actual output, by using the difference between actual output and the predicted output, we have to correct it. Okay. So the prediction accuracy can be improved by utilizing the latest measurement in the prediction. Prediction accuracy can be improved by utilizing the latest measurement in the prediction. This strategy is referred to as output feedback. This strategy is referred to as output feedback. A typical approach to add a bias correction B of K plus J to the prediction. We can write it as B of K plus J is equal to, up to this point, B of K plus J is the generalized representative, the jth instant bias B of K plus J is equal to Y of K minus Y cap of K, because I told you the difference we are because we don't have Y of K plus 1, Y of K plus, because that one is actual output and the given system is quotient. So we can measure the scalar quantity of the difference between actual output and the predicted output, the scalar quantity only, the current difference only. Okay, so we can write the bias correction B of K plus J is equal to Y of K minus Y cap of K. It is equation number 30. So also it is also referred to as residual or estimated disturbance. It is known as residual or estimated disturbance. So Y cap of K is one step ahead prediction made at the previous sampling instant K minus 1. So please note this Y cap of K is actually one step prediction predicted at the previous sampling instant K minus 1. That is also very important. At a previous instant, that Y cap of K is predicted, and that one is used to measure the residue at the current instant. So the corrected prediction, small, here we are using small Y, means the J step ahead prediction only, not multi prediction. So the corrected prediction Y nu of K plus J is defined as Y nu of K plus J is equal to Y cap of K plus J plus B of K plus J. Means by using this difference, this value is modified into this value. So Y nu of K plus J is equal to Y cap of K plus J plus B of K plus J. Okay. So we can write Y nu of K plus J is equal to Y cap of K plus J plus the scalar difference Y of K minus Y cap of K. So it is equation number 32. Okay. So the vector representation of bias correction is, means if you are actually we predicted P next values. So we have to correct all these P next values. It is known as P horizontal prediction. So the vector representation bias correction of that P horizontal, capital Y nu of K plus 1 equal to S into delta U of K plus Y cap 0 of K plus 1. Okay, so this one is the multi prediction up to this point. Now we have the correction plus Y of K minus Y cap of K into I. Why we are using I? The reason is this Y nu of K plus 1. This is P by 1. This is P by M into M by 1. So this multiplication is P by 1. This is also P by 1, but what about this element? This is 1 by 1. Actually the position is here. Okay, so this one must be P by 1 and all elements are 1. This is actually a p vector, p elements of a column vector with 1. Okay. So I is used to convert this scalar quantity to a vector. So y nu of the multi-prediction, the corrected multi-prediction y nu of k plus 1 is equal to s into delta u of k plus y cap 0 of k plus 1 plus y of k minus y nu of k, sorry, y cap of k into I. Okay. So now here please note this I is a p dimensional column vector with each element having a value of 1, that's I. So means the same correction is made for all p predictions. Same correction is made for all p predictions. So here y nu of k plus 1 is nothing but the column vector y nu of small y nu of k plus 1, y nu of k plus 2, etc. up to y nu of k plus p. Means it is similar to y cap of k, capital Y cap of k plus 1. The only difference is this is corrected predicted output. So please note this one is the widely applied method. This bias correction is widely applied method. Result is excessively sluggish response for a certain classes of disturbances. Okay. Now I told you in previous section, if you are using step response model, the system must be stable, first thing. And what is the second problem? Actually, directly we can't use step response model to non-self-regulating process directly, but with a slight modification we can use it. Okay, thus non-self-regulating, the best example for non-self-regulating process is integrating process. Okay. So the standard step response model is not appropriate for an integrating process because its step response is unbounded. So taking output right chain will eliminate this problem. What we have to do, instead of considering the actual output, take the differentiation of that output because it is integrating. So take its differentiation dy of k by y of k is a discrete version. In continuous version, instead of taking y of t, take dy of t by dt. Okay, that is delta y of k. So by taking delta y of k instead of y of k, we can avoid this problem. So delta y of k plus 1 is equal to y of k plus 1 minus y of k. Delta y of k plus 1 is equal to y of k plus 1 minus y of k. So if there are any numerical students, don't confuse with the symbol delta. Actually in numerical method this delta is actually used for forward difference. Del is used for backward difference. So here this one is the forward difference, but here the backward difference is used. So don't confuse with that. In this particular thing, just follow this one. Delta y of k plus 1 equal to y of k plus 1 minus y of k. Okay. So that one is equivalent to differentiation. Now it is bounded. Now what we have to do, wherever we have y cap of k plus 1, y nu of k plus 1, replace it with delta y cap of k plus 1, delta y nu of k plus 1. So replacing y cap of k plus 1 in equation by delta y cap of k plus 1. What is delta y cap of k plus 1? It is equal to y cap of k plus 1 minus y cap of k. So what we can write? We can write delta y cap of k plus 1 is equal to sigma I equal to 1 to n minus 1 si into delta u of k minus I plus 1 plus Sn into u of k minus n plus 1. Now we can replace this delta y cap of k plus 1 with this term. So it will become y cap of k plus 1 y cap of k plus 1 equal to y cap of k plus sigma I equal to 1 to n minus 1 si into delta u of k minus I plus 1 plus Sn into u of k minus n plus 1. So you can see that the one step ahead prediction used for a normal process and the integrating process have a slight difference. What is the difference? Here we have an additional term y cap of k. In normal process that is absent. That's a slight modification. So this slight modification we can extend basic multi-predictive control model for integrating process. Okay. Now similarly we can do bias correction. So bias correction, I'm very sorry. Like this way, we can't do bias correction. That is not possible. So, bias correction approach is not valid for integrating process. Okay, several modifications are available, but that one is not as simple as the prediction. That is not possible. Okay. Now, similarly, if we have, I told you disturbances are there, some disturbances are not measurable, but if disturbances are measurable, if some disturbances are measurable, then I told you we can consider as an input. So, if a disturbance variable is known or can be measured, it can be included in the step response model. So, already we have U, similarly we have disturbance, right? So let D denote the measured disturbance. So please note, let D denote a measured disturbance, and SID, earlier we used SI is the step response coefficient. Now here we are using another coefficient. SID is the step response coefficient due to the disturbance. Okay, so we have SID. Now we can modify the J step prediction as y, or one step prediction as y cap of k plus 1 equal to sigma I equal to 1 to n minus 1 Si into delta u of k minus I plus 1 plus Sn into u of k minus n plus 1. This is corresponding to input. Now the similar term corresponding to disturbance, that is sigma I equal to 1 to nd minus 1 SID delta d of k minus I plus 1 plus SND d of k minus nd plus 1. So here please note some disturbance, some differences. nd is the nd horizon of disturbance. Okay, like the and this is the nd horizon of disturbance. The important thing is here this P must be greater than or equal to nd also. That is also very important. Okay. So please note the modified equation is y cap of k plus 1, it is one step prediction, is equal to sigma I equal to 1 to n minus 1 Si delta u of k minus I plus 1 plus Sn u of k minus n plus 1 plus sigma I equal to 1 to nd minus 1 Sid delta d of k minus I plus 1 plus Snd d of k minus nd plus 1. Okay. So nd is the number of step response coefficients for the disturbance variable, step response 1e for the disturbance variable. So in general nd is not equal to n. In general nd is not equal to n. So predictions made more than one step ahead require an assumption about future disturbance. We need some assumption about future disturbance. We are not calculating. That is the difference between input and disturbance. If it is disturbance, we are finding the next input required for the system, but we are not finding disturbance required for. Actually, disturbance is not a required one. So there is a difference between these two terms. Okay. So we have to assume it. If you are not using or if you are not finding it, we have to assume it. We have to assume about the future disturbance. Okay, so we are now going to discuss about predictions for MIMO model. It means how to convert a single input, single output model to multi-input, multi-output model. So predictions for MIMO, multi-input, multi-output models. So it's a small section. So analysis for single input, single output system can be generalized to multi-input, multi-output system by using the principle of superposition. Okay. So for explaining purpose, consider system with two input U1 and U2 and two outputs Y1 and Y2. Okay. So the predictive model consists of two equations and four individual step response model, one for each input output file. Okay. So please note we have two input and two output means we have four individual step response model. So we can write y1 of k plus 1. We have two output. The first output, take the first output, is one step ahead prediction y1 cap of k plus 1 equal to sigma I equal to 1 to n minus 1 S11 I delta u1 of k minus I plus 1 plus S11 and U1 of k minus n plus 1 plus sigma I equal to 1 to n minus 1 S12 I delta U2 of k minus I plus 1 plus S12 and U2 of k minus n plus 1. So here just go through this equation. This first two terms is corresponding to input U1 where S11 S11 means corresponding to first input first output pair. S11 comma I is the step response coefficients of a step response model with input U1 and output Y1. Similarly, the second two are corresponding to U2 where S12 is the S12 comma I are the step response coefficients of a step response model with the input U2 and output Y1. So first one corresponding to output Y1 and second one is corresponding to input. Okay. Similarly, we can write second output y cap of y2 cap of k plus 1 equal to sigma I equal to 1 to n minus 1 S21 I delta U1 of k minus I plus 1 plus S21 comma n U1 of k minus n plus 1 plus sigma I equal to 1 to n minus 1 S22 I delta U2 of k minus I plus 1 plus S22 n U2 of k minus n plus 1. So equation number 38 and equation number 39 are the one step ahead predictions of y1 and y2 respectively. So the upper limit can be specified differently if settling time inputs are different. So here we assume that the settling times are equal. For different step response model, especially for y1 and y2, in some situation the settling time may be different. And if that difference is very large, we have to separately set the upper limit. One case we have to use n1 minus 1, in second case we have to use n2 minus 1. Okay. So convenient to express multi-input, multi-output step response model in vector matrix notation. We are directly going to vector matrix notation. So let the output vector is, now define the output vector as small y is equal to y1 y2 etc. ym transpose y is equal to y1 y2 etc. ym. Similarly, the input vector is u equal to u1 u2 etc. ur, means we have m output and small m output and small r input. So the character prediction, I am directly going to explain the character prediction, not the simple prediction. Character prediction of multi-input, multi-output system can be expressed in matrix form as y nu of k plus 1 is equal to s delta u of k plus y cap 0 of k plus 1 plus y of k minus y cap of k. Here I forgot to add I here. Sorry, here I. So y nu of k plus 1 is equal to s into delta u of k plus y cap 0 of k plus 1 plus y of k minus y cap of k into. Now what is the size of all these terms? Here y nu of k plus 1 is empty because you can see that small y is y1, y2 etc. ym. Okay, so this is small y. So what about y cap of k plus 1 is equal to y1 k plus 1 y2 k plus 1 etc. y m cap of k plus 1. This one is a one step ahead prediction. So like we have p different predictions. So if you are considering all these prediction simultaneously, it is multi prediction and here the output is a multi output. So if you are considering multi prediction for multi output, what it is? We can write it as y cap of k plus 1. Now the interesting thing is it will become y1, that is first output and its first prediction. Okay, so I simply can write y1 of k plus 1, y1 cap of k plus 1, y1 cap of k plus 2 etc. y1 cap of k plus p, that is P predictions of first output. Similarly, etc. We have ym cap of k plus p. So each variable have p elements. Such m elements are there. So this size will become mp into 1. So this is mp into 1. Similarly, what about u of k? I told you actually delta u of k is equal to u of u, instead of this, please note we have r input, so we have r difference also, so we can write delta u, small letter u of k is equal to delta small letter u1 of k, delta small letter u2 of k, etc. delta ur of k. Okay. Now, if you are considering m horizon of input, capital M horizon of input, then delta capital letter of u of k equal to, first take the first input, delta u1 of k, then delta u1 of k plus 1, etc. delta u1 of k plus m minus 1, etc. Now take the last input, delta ur of k plus m minus 1. Means we have r input variable, and for each input variable we have m horizon. So the total size of this vector is small r capital M into 1. So this is small r capital M into 1. So what about S? S is a mp into rm vector matrix. Okay. So please note this y cap of k plus 1 is small m into p, delta u of k is small r into capital M. So S is, this S term is small m p into small r capital M. Okay, the size of y cap, all y are same. Okay, this is 1 by 1. So we have to convert this y 1 by 1 to m into p. So here we have I, but the size of I is m into p into 1. Okay. So this one is the modification that we have. So y similarly, so y nu of k plus 1 is equal to, so here in this particular case y nu of k plus 1 is nothing but column vector of y nu of k plus 1, y nu of k plus 2, etc. y nu of k plus b, where each y nu have m elements. M elements are there. Okay, m small m column elements are there. So here please note that y cap 0 of k plus 1 is the mp dimensional vector of predicted unforced response, and is y cap 0 of k plus 1 equal to column vector of y cap 0 of k plus 1, y cap 0 of k plus 2, etc. y cap 0 of k plus p, where each y cap 0 is nothing but y1 cap 0, y2 cap 0, etc. up to ym cap 0. So delta u of k is the Rm dimensional vector of next m control move. We already discussed about that. So delta u of k equal to column vector of delta u of k plus 1, etc. delta u of k plus m minus 1, but each u element have u1, u2, etc. up to u, or column vector u1, u2, etc. up to u r. So now last one is dynamic matrix X, that is equal to, now in this particular case S is equal to S1 0 0 0, S2 X, similar to that. There is the interesting thing is the size of each S is different now. Okay. So here Si, take each S element. Each S element is the M by R matrix. Each element, if you are taking this element, this is M by R. Means if you are considering each row element, m elements are in each element, m rows are there in each element, so such p elements are there. So if you are considering entire row, p into m or m into p elements are there. Similarly, if you are considering each column, okay, so take each column, to take a particular column, the first element have r column element, so and such m elements are there. So m into r elements are there in a particular column, in a particular row. Okay, if you are taking a particular row, that is here. Here we have m into sorry r into capital M elements are there. And if you are taking a particular column, we have small m into p elements are there. Okay. Now, if you have an algorithm and if you are able to calculate each value recursively, it will reduce our task. Otherwise, each time we have to calculate the entire structure. By using the previous value, if you are able to find the new value, it is very easy for us, is it? So, the recursive relation for the predicted unforced response that we are going to discuss here. So, for a stable model, the predicted unforced response can be calculated from a recursive relation. Actually, y cap 0 of k plus 1 equal to m into y cap 0 of k plus s into or s star into delta u of k, not s star into delta u of k, where y cap 0 of k is the column elements of y cap 0 of k, y cap 0 of k plus 1 etc. y cap 0 of k plus p minus 1 means the p prediction horizon of that unforced y cap 0 of k. M is equal to 0 im 0 0 0 0 im dash 0 etc etc. The last two rows are similar 0 0 etc 0 im 0 0 dash etc 0 im. S star is equal to S1 S2 etc SP minus 1 in last element is SP. A single row, we are considering a single row. Okay. So this is the recursive equation. I am not giving much explanation about this one. Okay. So now please remember currently most of the multi-prediction control research is based on state space model, because what is advantage of state space? It is providing an important theoretic advantage, that is best framework we have for both linear and non-linear control problem. We give a best framework, so that one is an advantage. And state space models are also more convenient for theoretical analysis also. Okay.